Hello everybody, welcome to the last video in the series of Physics at Home. In this video we're going to talk about buoyancy. Here's a demonstration of what's going on. Right now what we have is a steel ball attached to the spring. Now we have seen this before in our Hooke's law simple harmonic motion lab. Right now the weight of the steel ball is equals to the force from the spring. That is leading to stretching the spring by whatever this length is. Okay. Now let's see what happens if we submerge this steel ball in water. Watch the spring. As you can see, the spring is not as stretched as it was before. And if I lower this, the spring gets stretched again. So what's going on is the water which the steel ball is displacing, the volume of it and the weight of that water is equals to the force that the water is applying back on this steel ball and holding it up. That force is what we call the buoyant force. And what we want to do is now measure the two lengths before submerging and after submerging. So let's see. Before submerging, okay, so make it steady, and this turns out to be 21.6 centimeters. And after I submerge, we use 0 here, so get submerged now. And bring it down here. It is about 19 centimeters. Yeah, so 19 centimeters. So 21.6 is before and 19 centimeters is, after submerging. The difference between the two is how much is the force, the buoyant force that the steel ball, the water is holding the steel ball up. And that buoyant force is related to the volume of the steel ball, for which we're gonna need the radius. And if you remember from the first video, you can wrap the tape around the steel ball and get the circumference divided by 2 pi gives the radius of the steel ball. Then we would use to calculate the volume of the steel ball. Okay, and the force, buoyant force, is related to how much ever is the difference between the two lengths, and the difference between the two lengths, and then the spring constant K, that will give us the force. And from that force, as we said, that force is equals to the weight of the water that the steel ball displaces. So the displaced water's weight is equals to the buoyant force. And using that, we're going to calculate the density of the water. And we're going to see how close it gets to the actual density of 1000 kilograms per meter cube. The setup here shows the steel ball attached to the spring. So right now, weight is the mass of the steel ball multiplied by gravity, and it stretches the spring by some distance, here x1, let's say, and that results in force of the spring pointing upwards, correct? So let's call this as F1 here. Now this is a situation where it's just the spring and the steel ball, correct? And then weight is equals to the force from the spring. So those two forces balance each other out. But when we submerge the steel ball in water, then the spring's length reduces to distance x2. Okay. Now think about it here. Right now, the weight is still mass of the steel ball multiplied by gravity, correct? Mass of the steel ball multiplied by gravity. But now look at this, now, since the spring is now shorter, that would mean the force 2 here is smaller than the force 1, which we can also see by the lengths of the arrows. So there has to be, more pull downwards. But we're saying that at this position, the steel ball stays at that same point, right? So meaning there has to be something holding it up. And that turns out to be the buoyant force. So I'm going to call this F subscript P. This buoyant force leads to the change or the delta X here, which, holding that spring up by whatever that amount. And this buoyant force is nothing but what the water which was present where the steel ball is now, but it has been displaced. So the volume of the water, okay, that's, gets pushed out, by the steel ball, is trying to go back in. And that water, how much ever is the weight that was present, at the steel ball, that weight of the ball is how much is the buoyant force. Okay, so the buoyant force equals to weight of the water which got displaced by the steel ball. Okay, so how much, it's going to be the weight of the water? Well, we know the force, the buoyant force is what is causing the delta X, right? That is, holding that spring, slightly up compared to its initial position. So we can go back to our Hooke's law. The force from the spring equals to K delta X, right? And in my earlier video, I got the K1 and K2 using Hooke's law and simple harmonic motion respectively. The spring constant, the average of the two, was 3.246 Newton per meter. Okay. Now in the data here, X1 was 21.6 centimeter, and X2 was 19 centimeters. So the delta X was 21.6 minus 19 gives me 2.6 centimeter, which is 2.6 10 to negative 2 meters. Okay, so let's calculate the force from the spring, for that delta X, which is nothing but the buoyant force. So 3.246 times 2.6 10 to negative 2, and that turns out to be 8.44 10 to negative 2 newtons. So this is the difference, right, between the first force from the spring and the second force from the spring, right? And that difference is caused by the water holding that steel ball up. So FB, which is the weight of the water displaced, is 8.44 times 10 to negative 2 Newton. Now weight of the water is equals to the mass of the water multiplied by gravity. Yeah. So let's calculate mass of the water. So weight of the water divided by 9.8 gives us the mass of the water, and that would be 8.612 times 10 to negative 3 kilograms. So which is like 8 milligrams of water. Okay. Now here we are gonna introduce what is called as density. Density, we use symbol this, which is a Greek alphabet called rho, is equals to mass over volume. So this formula indicates, how packedly closed, the atoms or molecules of a substance are over a given volume, right? So we know the mass of the water. Can we calculate the density of the water from this? Well, we need the volume of the water, correct? And using the tape, wrapped around the steel ball, I was able to measure the radius of the steel ball. And the radius of the ball was 12.68 millimeters, which is 12.68 into 10 to negative 3 meters. That was the radius. Now steel ball is, it's a sphere, right? So volume of the steel ball is given by this formula, 4/3 pi r cube. So let's calculate volume of the sphere. And it is 4/3 times pi times radius, which is 12.68 exponential negative 3 cube, and it is 8.5398 into 10 to negative 6 meter cube. That was the volume of the steel. That's the volume of the steel ball. That is the same volume of the water that got displaced. Correct. Now using the mass of the water and the volume of the water, now we can calculate the density of the water. So density will be mass, which is 8.612 times 10 to negative 3 divided by volume, which is 8.5398 10 to negative 6, and this turns out to be 1008.5. This is kilograms per meter cube. And the standard density of water is, so the standard, which is 1000 kg per meter cube. So you can see how close, really close these two are. And the difference between the two is just 8.5, right? And then if you do the difference divided by what is supposed to be, the standard, right? So 8.5 over 1000 multiplied by 100, gives us percent error to be 0.85. It's pretty close. So our understanding that the water was there at the steel ball got displaced, and that water, whatever the weight of that water was, is equals to the buoyant force that was holding that ball up. And this right here is the lab for buoyancy. So I hope you enjoyed these series of videos. Have a good one.